So, continuing into chapter 6, I am on section 6.1, and this is where we start going over power series and the functions associated with the power series, such as finding whether it converges or diverges, um, transforming a function into the power series format in which you can conduct these tests to test for convergence or divergence. That is pretty much what 6.1 is centered around. Starting at like the beginning, a power series is typically just a series that's in the form of c times x to the power of n, where c is a constant, and x to the power of n is actually the important factor in this. One thing that we did look at before that I was actually confused on before tonight, actually, it was I did think that since -1 to the power of n was a power, it could be represented using a power series, but no, that is specifically used as an alternating series, and you cannot use the power series convergence or divergence tests or like rules on a alternating series. There are two different things, and if it's in the form of x to the power of n, then it is a power series, but if it's specifically in the form of -1 to the power of n, then it is a alternating series. So back to the power series, it is just defined as a series from n to infinity where c sub n times x to the power of n equals a series that is it's a power series that is centered at x equals 0 technically. If there is a radius, then we would use the same formula, the series from n to infinity time where the series is c sub n, and if there's a radius that is specified, then it would be x minus a to the power of n instead of just x to the power of n. And this just means that the radius a impacts how the chirality of the function is, like where it is rotated around or reflected around. And if it's not at x equals 0, which is just the x-axis, then we do need to specify in what direction we would need to move for the radius that it would start, that the function would actually be centered around that point instead of x equals 0. So moving on to testing for convergence of this type of series. So say that we just go with the extended equation of a power series, the summation from n to infinity of c sub n, and then in parentheses x minus a to the power of n. So if we just use that extended formula and we consider one of these following conditions, then we can determine whether the power series converges or diverges. The series actually converges at x equals a and diverges where x does not equal a. If the series converges for all, the series should converge for all real numbers x, and there or there will exist a real number that the series converges at if x minus a is less than that real number, then it converges, and if x minus a is greater than that real number r, then it diverges. And if x minus a equals r exactly, then it may converge or diverge. You might need to pick another real number to test that out around. And one thing I did forget to mention is for that third condition where you're testing around a real number r, every time you test around that, it's always the absolute value of x minus a. So those are the conditions for testing for convergence specifically in a power series. If any one of those three conditions are met, again, a power series will converge, except for that third condition where I mentioned where it would diverge. Moving forward, the only other aspect of this is finding like the interval, like the radius of the convergence. So the way you would do that is you can pretty much use one of the comparison tests. Like say we have the summation of x to the power of n over n factorial to the power of n. Like if we do the ratio test, we can calculate that p by calculating the limit of a of n plus 1 over a of n, and then reducing that down until we get a p value, and from there we can check whether or not it converges or diverges. If the series converges for all real numbers x, then the interval would just be negative infinity to infinity, and the radius would just be infinity since it goes infinity ways both ways. So if the series doesn't converge though, like let's say the series diverges and it's centered at 0, if it diverges, then the radius would just be 0 because it doesn't converge on the interval at all. The convergence interval is only for convergence, of course. And the only other thing is you can rewrite equations to represent the power series general form. That way you can follow these assumptions when conducting the convergence or divergence tests, and that will also be one of the things that we need to add to the list of deciding which type of test to use to test for convergence or divergence of series. And I believe that is the conceptual side of 6.1. Of course, it's much better to actually get into practice, so I'm going to start here, section 6.1, question 41, and I believe that was also on the list of original practice problems, but I just did not get around to doing that one, so I'm going to do it now. The first question is, in the following exercises, given that 1 over 1 minus x equals the series x to the power of n with convergence in the domain -1 to 1, find the power series for each function with the given center a and identify its interval of convergence. So question 41, the function that we're given is x squared over 1 minus 4x squared, and where a equals 0. Okay, so we luckily don't have to rotate this around any other axis since it's already centered around 0. So the first thing we're going to do is I'm just going to rewrite it, x squared over 1 minus 4x squared, and then what we're trying to do is we're trying to get it into the format where it's something x to the n, something x to the n. And we can see that 1 over 1 minus x equals x to the n. So we need to get this where it's in the format 1 over 1 minus x. So in order to do that, we need the x squared out of there. So so I guess what we can do is try to factor out the x squared. So this would equal x squared on the numerator times 1 over x squared times 1 over x squared minus 4. Factor out the x squared would just be 1 over x squared minus 4. Minus x. I don't think that's actually going to factor out properly. So far I've done this, but in the denominator I have 1 over x squared minus 4, so I'm going to try to refactor this. Well, 1 minus 4x squared is actually a perfect square, I believe. Yes, it is. So it would be x squared over x squared, 4x squared plus 1, 4x squared plus 1. X squared would be 2x. 2x plus. No. It would be 1 minus 2x times 1 plus 2x. So I'm actually simplifying x squared over 1 minus 4x squared to x squared over 1 minus 2x times 1 plus 2x. That way we can at least simplify out the x, and what we can do now is I'm just going to try to simplify it a little bit more. So I'm going to try to factor out the 2 from the bottom. So this is going to be x squared over 2 times negative x plus a half times 2 times x plus a half. And that way we can at least combine the 2's outside of the actual inner equation. So what we have here is this equals x squared all over 4 times x plus a half negative x plus a half. And I know you're supposed to expand it again so that you can have 2 terms, possibly the c sub n term, and then just the x to the n term. So right now, what we're dealing with is we're trying to get this into at least 2 terms, since there is a numerator and a denominator, and I don't think it's going to cancel out really. I'm just going to try to distribute this x squared over 4 times negative x squared. Actually, I did not factor that correctly. This actually equals x squared over 4 times squared to x squared plus 1 plus 1. So far I'm at x squared over 4 times negative x squared plus 1/4, or 4 times the whole of negative x squared plus 1/4. If I distribute this now, I get to x squared over negative 4x squared plus 1. And I think if I get to the, what's that form? The 1 over 1 minus x form, I can simplify that into x to the power of n. So what I need to do now to get that into this form is 1 minus x on the bottom. Well, currently right now I have x squared over 1 minus 4x squared. So I need to get it down to just x, which means I would need to divide by 4x. Okay, so since we are at x squared over 1 minus 4x squared, I think we can say that this technically equals x squared over x squared times oh, we can say that this equals x squared times 1 over 1 minus 4x squared. So now all we need to do is get the x isolated. So all we need to do for that is, this is still perfect square. I realized I just went back in a circle. I'm back at the denominator being 1 minus 4x squared. So I'm actually gonna retract all the way up to when I was factoring out for the first time. I'm gonna go back to the step where I had x squared over going back all the way up there where I had x squared over 2 times the negative x plus a half and then 2 times x plus a half, and I'm gonna see if we can get to a better way to factor this out. Well, we can still keep the 4, so x squared over 4 times negative x plus a half times x plus a half. Okay, so I found one example is modeled similar to this, so I'm going to try to follow that lead and get it down to where I have a 1 minus something squared term and then an x squared over something term, because currently I'm at a standstill. So I think what I can do is this equals x squared over 4 times whatever this FOILed out is, and this FOILed out is x squared times negative x squared, negative 2x to the fourth, nothing, plus 1/4. So that's this is the term, plus 1/4. So far I got one of the terms. I got the x squared over 4, and then that is the remaining term that I'm trying to simplify down into a power series general form. Um, and then I'm actually going to multiply this entire poly by 4 to get x squared times negative 8x to the fourth plus 1, about 1 minus 8x to the fourth times x squared. We wanted something to the n, so I'm on the verge. I feel like I'm missing like one step to get into that final power series equation. So I'm trying to look at another example from the section 6.1 book, but I'm unsure in which direction to move. Well, technically, I can put it in the form right before this. If it's x squared over 4 times this, then this should technically equal out to x squared over 4 times we have to put this in the form 1 minus x squared over something. So if this is 1, what times this times 8. No, no. So what times that equals 1? 4th minus 4th minus 2x to the 4th. We need to get it in squared format. So times what? So take out 1/4, and then that would be 1 minus I'm gonna keep trying this. I'm going to try to expand out this function one more time. So it would be x squared over 4 times negative 3 halves plus 1 plus x times 1 minus x minus a half. So instead of trying to put it back together after the 4 times the x squared plus a half, negative x plus a half, I expanded it out one more time to where it would be x squared over 4 times negative 3 halves plus 1 plus x times 1 minus x minus 1 half. I figured I'd do it this way because at least on one of the sides it has the 1 minus x component. So the next thing I'm going to do is I'm actually going to leave the side that has the 1 minus x component alone, and I'm going to what did I do? Oh, I'm sorry, I read that wrong. I completely miswrote this step. So the one step I forgot to say is after x squared over 4 times x squared plus a half times negative x squared plus a half, I simplified it down one more step. I got it down to x squared over 4 times x plus 1 minus a half times negative x minus 1 plus a half. I figured I'd do it this way because the way the factorial works is right now the denominator power is in like it's it needs to be factored down so that we can get the terms to put into the power series. So once I did that, then I simplified down the ratio where it would just be x squared over 4 times negative 3 halves plus 1 plus x times 1 minus x minus a half. So I know it's a little bit messy, but this is my work so far. And after this, I went there, and then I simplified that denominator down to this denominator. And then from here, I actually am having a lot of trouble figuring out how to simplify this down, so I am gonna consult the textbook a little longer after I take a quick break because this has been a pretty long recording. But once I resume the pause, I will continue working on this one. Thank you. So I'm back. Unfortunately, it I just could not figure out how to simplify this, so I did try to look up similar examples, and I found one which had a similar denominator, and I found that there's actually a closed form, like a closed general form, like Maclaurin series, Taylor series, like how they have a closed form version of stuff. I found the closed form version of the denominator, and since the top is just x squared, the other one was just x, um, I realized that the f of x function with this denominator, and again, I still do need to learn how to properly factor this out, but for the meantime, what I got was the closed form. The power series of this is f of x equals 4 to the power of n times x to the power of 2n plus 2. Right there. And now comes, I guess, the final part of this. What we need to do is we can do the limit test. We can just set a of n equal to 4 to the power of n times x to the power of 2n plus 2. And then we can set a of n plus 1 equal to 4 to the n plus 1 times x to the 2n plus yeah, 2n plus 2 plus 2. So 2n to the 4 plus 4. So right now what we have is an equals 4 to the n times x to the n plus 2, and then an plus 1 equals 4 to the n plus 1 times x to the 2n plus 4. So all we have to do is put an plus 1 over an, and what we get with that is an plus 1 over an equals 4n plus 1 times x 2n plus 4 all over 4n times x 2n plus 2, and then well, I mean, in the 4n plus 1 over the 4n, the n's cancel out, so it's just 4 to the first, and then it's just 4 to the first on top, and then on the bottom the two n's cancel out as well, and then you can just subtract the exponents, so it would actually just equal 4x squared. Well, the absolute value of 4x squared. And then if we, I guess if we solve for that, x could be, like if we set it equal to 0 and we solve for that, sorry, not set it to 0. We need, so it's just the x term that's cubed, so it would just be x equals a half or a negative half because it's the absolute value at the end of it. So the interval would be -1/2 to 1/2. And that's the interval of convergence, actually, not the radius. I apologize. That's the end of my work for section 6.1, question 41. It was probably the most challenging problem I've done for this problem set, but I'm going to take another look at it by myself and kind of catch up on it if I do need some extra practice, because that was also one of my trouble spots on the exam, like converting a function into a power series function and then going through that limit comparison test to figure out what the interval of convergence is. Like, I didn't do all of that on the final exam, and I do have a much better understanding now, but the main part that I struggle with is factoring out these equations, because I need to remember some of the closed forms and how to get into there. But I hope that was um, I hope that was a good recap of 6.1. I don't believe I forgot anything, and I apologize for the question taking so long. It truly was a difficult one. Thank you.